In this session, we will discuss about amplitude modulation. Let us see what is the definition of amplitude modulation. Amplitude modulation is a process of varying amplitude of the carrier in accordance with the amplitude of the baseband signal. See, baseband signal is also called a modulating signal. And in the case of amplitude modulation, frequency and phase of the carrier remains constant. That means in the case of amplitude modulation, typically there will be a modulating signal which is shown here, which is a sine wave, and there is a carrier signal which is also another sine wave, but you can see in the diagram the frequency of the carrier signal is higher comparing to the frequency of the modulating signal. And these two signals will be given to a modulator, that is AM modulator. As a result, it will produce amplitude modulated wave. You can see that this wave is the amplitude modulated wave and its envelope is this one. See, this envelope follows the original information signal. See, information signal is modulating signal and the amplitude modulated wave follows the envelope of the original modulating signal. See, you can see both the envelopes are similar to the original modulating signal or baseband signal, and inside this envelope there is carrier frequency, see here, and whose amplitude is varying in accordance with the modulating signal. That is why it is shown like this. So suppose this is the modulating signal which is shown here and its amplitude is EM, that is also shown here. Amplitude of modulated signal is EM, this is the amplitude, and carrier signal is shown here. This is the carrier signal and its frequency is higher comparing to the modulating signal, and both these signals are sine waves. Difference is that their amplitude and frequency are different, and here the EZ is the maximum amplitude of this carrier signal, and this is the amplitude modulated wave. You can see in the diagram that the amplitude modulated wave contains the carrier signal whose amplitude is varying in accordance with the original modulated signal. See here, this is the carrier signal and its carrier signal's amplitude is varied in accordance with this modulating signal. So its envelope will be like this. Similarly, you can see that in the lower portion also the carrier signal amplitude follows the baseband modulating signal. That is why it will get this shape. So this is the envelope, and you can see the various amplitudes in this AM modulated wave as this amplitude. This is the maximum amplitude and this amplitude is carrier amplitude plus modulating wave amplitude, that is EC plus EM is its amplitude, and at this portion the amplitude is EC minus EM, that means carrier amplitude minus modulating amplitude is its value, and these frequencies represents the unmodulated carrier wave. See, we will explain about the frequencies of this amplitude modulated wave in the next slides. So we can see what is unmodulated carrier and modulated carrier, etc. So this simply represents the unmodulated carrier, that you just remember, okay. Next, we can derive an expression for or mathematical equation for the amplitude modulated wave. See, in the figure you can see that this is a sine wave and its magnitude, maximum magnitude is EM. So we can derive an expression for this modulated signal. Simply it is a sine wave, you know that, and suppose its frequency is FM, or that means M indicates the modulating signals, F is the frequency. So we can write the equation for this sine wave as its maximum amplitude is EM. So we can write the instantaneous value of the modulated signal as EM equal to maximum amplitude EM into sine omega M into T, where omega M is the angular frequency and it has an equation 2 pi into Fm, where Fm is the frequency of the sine wave and EM is the instantaneous amplitude of the modulated signal. Capital EM is the maximum amplitude of the modulated signal, that you can see in the figure. This EM is the maximum amplitude and frequency is Fm and angular frequency will be 2 pi Fm, and instantaneous value of this sine wave is obtained by this equation, that is EM equal to EM sin omega M into T. Similarly, we can write the equation for instantaneous value of the carrier signal. See, this is the carrier signal and its frequency is we can represent as Fc. Similarly, its angular frequency will be omega c, and omega c is equal to 2 pi into fc, and its maximum amplitude is ec. So we can write the instantaneous value of the carrier signal as ec equal to capital EC into sin omega ct, where capital EC is the maximum amplitude of this carrier signal and omega c is the angular frequency of the carrier signal, and it has a value omega c equal to 2 pi into fc. So once we have the two equations, we have to derive the equation for the amplitude modulated wave. We know that amplitude modulated wave is obtained by modulating this carrier signal by this modulating signal. That means the carrier signal amplitude is varied in accordance with the modulating signal. So there will be some changes in the carrier signal with respect to the modulating signal. So we have to derive the expression for this signal. Okay. So we can write it as the instantaneous value of the amplitude modulated signal will be, we can write it as EAM will be the instantaneous value. So it will be equal to, there will be a peak amplitude for that signal. So its peak amplitude is EAM, capital EAM, that is represented here. And we know that from this figure, you can see that its frequency is the carrier frequency, right? EC is the frequency. Suppose FC is the frequency of this carrier signal. This signal also has the similar frequency like this carrier signal, right? See, you can see the signal here, and here the frequency of this signal is similar to that, or somewhat similar to that of this carrier signal. So we can simply write it as the instantaneous value of this signal will be equal to maximum amplitude of this carrier signal, amplitude modulated signal into sin omega ct. So next we have to find out what is this maximum amplitude EAM. So we can write EAM will be equal to, maximum amplitude of this signal will be, EAM will be equal to EC plus EM. What is EC? EC is the maximum amplitude of the carrier signal, and that amplitude will be added with the instantaneous value of the modulated signal. That is, you can see from the diagram that this is the carrier signal, right? Its amplitude is EC, and to this EC, that is, this is EC, to this EC, this value is added, right? Which is this value? This is the instantaneous value of the amplitude modulated wave. So it is EM, small letter E suffix M. So we can write the maximum amplitude of the amplitude modulated wave is the carrier amplitude, maximum carrier amplitude plus the instantaneous value of the modulated signal. We know the instantaneous value of the modulated signal, which is EM sin omega M into T. That we have first written this equation. Though EAM equal to EC plus, instead of EM we can substitute EM sin omega M into T. So we can write the instantaneous value of the amplitude modulated wave EAM equal to, we have the equation EAM equal to capital EAM into sin omega ct. Instead of EAM we can substitute this value. Okay. So EAM will be equal to this EC plus EM sin omega M into T into sin omega ct. We can multiply this sin omega ct with the terms which is inside the bracket. So EAM will be equal to EC sin omega ct into EM sin omega ct into sin omega M into T. And here you can see that there is a relation which relating the maximum amplitude of the modulating signal with the maximum amplitude of the carrier signal, which is the modulation index. So modulation index M equal to capital EM divided by EC. That means it gives the ratio of the amplitude of the modulating signal to the amplitude of the carrier signal. In this relation we can write EM equal to M into EC. So we can substitute for this EM as M into EC. So this equation will become EAM equal to EC plus sin omega ct plus M into EC sin omega ct into sin omega M into T. Here you know that this is in the form of sin A sin B. There is a mathematical relation, that is sin A sin B can be converted into 1 by 2 cos A minus B minus 1 by 2 cos A plus B. So we can substitute for this sin A sin B as by using this relationship. So instead of this sin A sin B, we will get a cos term. So we can write this equation as EC sin omega ct plus MEC is a constant term, so MEC will comes there. Instead of sin omega ct into sin omega mt, this relationship we can substitute. So there will come a 1 by 2 and instead of this term cos of A minus B comes, that means cos of omega C minus omega M into T comes minus MEC by 2 into cos of omega C plus omega M into T. So this is the final equation for the modulated signal or AM signal, amplitude modulated signal. So this is EC sin omega CT plus MEC by 2 cos omega C minus omega M into T minus MEC by 2 cos omega C plus omega M into T. So this is the final equation for the amplitude modulated wave. And in this equation, EC sin omega CT is the carrier signal, and you can see this is the EC sin omega CT is the carrier signal. That means it has got a carrier frequency and its amplitude is EC. So this represents the carrier signal itself. And this is, you can see, its frequency is omega C minus omega M. That means its frequency is lesser than that of the carrier signal. And this frequency contains the information about the modulated signal. That means it contains the term omega M. That's why it contains some information about the modulating signal. Similarly, there is another term omega C plus omega M. That means this carrier frequency is modified with modulating signal. That means its frequency contains some information about a modulated signal, right? See, first term does not contain any information about the modulated signal, but in the second term there is some information about the modulated signal since there is an omega M term. Similarly, third term also contains some information about the modulated signal because it contains omega M term. So we can separate this as, this is the carrier component of the modulated wave and this is the lower sideband, this is the upper sideband, because here omega C minus omega M is the lower frequency comparing to the omega C. So we can say it as a lower sideband. Similarly, omega C plus omega M is the frequency term which is greater than that of omega C. That is why we are calling it as upper sideband. So in the amplitude modulated wave, there will be two sidebands which are lower sideband, upper sideband along with the carrier signal. Actually, the information is present in this sideband, that is in the lower and upper sideband. So you should by heart this equation, and this is the final equation for the amplitude modulated wave. So next we have to calculate the bandwidth of an AM wave. Bandwidth is measured by subtracting the lowest frequency of the signal from the highest frequency of the signal. So bandwidth is equal to the highest frequency of the signal minus lowest frequency of the signal. In the amplitude modulated wave, we know that there are two sidebands, that is upper sideband and lower sideband. We know that the upper sideband has a frequency Fc plus Fm and lower sideband has a frequency LSB is Fc minus Fm. Here LSB indicates the lower sideband, USB indicates the upper sideband. Upper means its frequency is high, that is why we are adding Fc plus Fm. Lower means there is a smaller value for the frequency, so we will subtract Fc minus Fm. So bandwidth is the subtraction of FLSB from FUSB, that is bandwidth equal to FUSB minus FLSB. We can substitute for FUSB as Fc plus Fm, and instead of FLSB we can substitute Fc minus Fm. So when we are subtracting these terms, two Fc terms will be cancelled out and finally we will get bandwidth equal to 2Fm. So it is an important relation and it will be useful for solving the problems. So in the case of an amplitude modulated wave, the bandwidth is 2 times of the frequency of the modulating signal. That is the information here. That is bandwidth is equal to the 2 times of the modulating frequency, that is 2Fm. Next we can draw the spectrum of the AM wave. You know that in the case of an amplitude modulated wave, there are 3 frequency components. One is carrier frequency, other is upper sideband frequency, next one is lower sideband frequency. So frequency spectrum can be drawn as frequency can be drawn along the x-axis and amplitude can be drawn along the y-axis. And we will mark the 3 frequency components. First one is the carrier frequency, that is Fc. We know that it does not contain any information about the modulated signal. And next we will draw the upper sideband frequency. We know that the frequency of the upper sideband is Fc plus Fm. So it will locate just to the right of this Fc. So Fc plus Fm will be here. So it can be indicated as FUSP. Similarly, another frequency component which is FUSP, which will locate to the left of this Fc. So we can write it as Fc minus Fm. And we know that these are the frequencies, but we doesn't know the amplitude. Let us have the equation. See, you have this equation. In this you can see that Fc has got the amplitude EC. Similarly, lower sideband has got the amplitude MEC by 2. Similarly, upper sideband has got the amplitude MEC by 2. So you can simply write the carrier frequency has got the amplitude EC and upper sideband has got the amplitude MEC by 2. Lower sideband has got the amplitude MEC by 2. So these are the this is a spectrum for the amplitude modulated wave, and it is a very important thing. So actually spectrum is indicated by drawing the frequency components in the wave, and we will mark the frequency along the x-axis and amplitude along the y-axis, and we will mark the frequency components. So in the case of amplitude modulated wave, there will be 3 frequency components. And next we can define the modulation index, which can be also called as modulation factor or percentage of modulation. We can write modulation index is the ratio of modulating signal voltage to the carrier voltage, and it is represented by the letter M, and we can write the equation as EM by EC. So practically the modulation index value lies between 0 and 1, and this modulation index is also known as modulation coefficient or depth of modulation or degree of modulation. And next we can explain the degrees of modulation. That is, actually we are explaining about the modulation index itself. There are 3 degrees of modulation. First is under modulation, critical modulation and over modulation. This classification is based on the values of M. That is based on the values of modulation index. Suppose M is less than 1. In this case, under modulation takes place. In such cases, EM will be less than EC. So you can see in the case of under modulation, this waveform will be looking like this. See, there is an envelope EM which has got a maximum amplitude EM, and in between this envelope there will be carrier signal. This is the amplitude modulated signal. And in the case of next case is critical modulation. In critical modulation, M equal to 1. When M equal to 1 means EM will be equal to EC. So what happens when EM equal to EC? When EM equal to EC, you can see that this is the EM value. When EM equal to EC means that this portion will be equal to carrier amplitude. So once we are drawing this lower portion will touch this x-axis or time axis. So when EM will be equal to EC, that means the lower part of the envelope in both sides will touch the time axis, so that there will not be any modulated wave in this portion. That means modulated wave appears only between these two times. So there will not be any modulated wave in this section. So some information will be lost in the case of modulation index equal to 1. So it is called the critical modulation. Next is over modulation. In case of over modulation, M will be greater than 1. In such case, M is greater than 1 means that EM will be greater than EC. So what happens when EM greater than EC? See, when EM is greater than EC means that this is EM. This portion is EM and this is also EM. When this portion is greater than EC means that this portion comes lower to this time axis, right? This portion coming lower to this time axis. Similarly, this portion also coming upper to this time axis. So the AM envelope will be distorted. Actually, the AM envelope should be like this. It should follow the modulating signal. But here, when EM is greater than EC means that the envelope of the modulated signal will be collapsed. That means it will be very difficult for the detection of such type of AM wave. So these are the 3 degrees of modulation, and this classification is purely based on the modulation index values. And next, another case when M equal to 0. M equal to 0 means that EM will be equal to 0. That means that there will be only carrier signal will be there. No message signal will be there. Actually, modulated signal means original information signal or message signal. And in order to transmit the message signal, we will have to increase the frequency. That is why we are modulating a signal, that you have studied in the need for modulation. So when we are transmitting a modulated signal with the carrier signal, it is desirable to transmit it with the modulation index value which is less than 1. When it is equal to 1, some information will be lost here, or if it is greater than 1, then the envelope will be distorted. If it is equal to 0, then there will not be any message information or message or information. So it is desirable to have a modulation index which is less than 1 for a good transmission system. There are some important equations which is used for solving the problems. Suppose if there are different signals, that means different message signals or baseband signals, and it is modulating the same carrier signal, so that it will give different modulation index such as m1, m2, etc. up to mn. Then the total modulation index will be obtained by the relation mt equal to square root m1 square plus m2 square plus etc. Similarly, if we have a modulating signal like this, and the different notations as, suppose Emax is the amplitude value from the time axis to the upper envelope. Similarly, E minimum is the amplitude from the time axis to the lower portion of this upper envelope. Then the modulation index can be obtained by the relation E max minus E minimum divided by E max plus E minimum. And these two relations will be used for solving the problem. So you should remember these two equations. Next, we can derive an expression for the power of an AM wave. That we will do in the next video. Okay.